I mean, I know that this is not exactly multi-scale of quantum mechanics, but it's somehow connected also with a part of the other discussions in the workshop, in particular about embedding, because I mean, in an open quantum system can be viewed as an embedding problem. But one difference is that instead of talking about ground state problems, I mean, this talk will be mainly about time-dependent problems, for which to some extent things are more well-defined because you do not worry about the well-posedness of these Luttinger-Work functionals, for example. But on the other hand, it's also more challenging because you have a completely different beast of sign problems, which is the dynamical sign problems, which I want to illustrate a little bit our understanding of this. And so this has been actually quite, I mean, it's a collaboration with Zhenning and his student Siyao Yang, which was like ongoing for quite a few years. But in fact, due to the pandemic, I never gave the talk. But I mean, I think it's actually the first time for many of you to hear me talking about inchworm Monte Carlo algorithm. So if there was anything that is unclear, I mean, since I never really talked about this before, just feel free to interrupt and ask questions. And I should mention that most of the work has done by the student Siyao Yang, who is an excellent student who graduated from National University of Singapore and who is now a postdoc in Zhenning's group. Okay, so and also that I'm not going to talk about applications. I really want to convey some of the mathematical understanding that we have for the problem, so that actually I will start even with an extremely simple example, just to try to convey the message. So, I mean, the simple example is just this. I mean, as simple as it. So it's kind of the usual Schrödinger equation, and you can, if you, I mean, you are like uncomfortable even thinking about Schrödinger equation, you can even think about this H as the 2x2 matrix. Okay, and so we have like a unitary evolution equation, and now, I mean, for the reason that will maybe become clear in the later part of the talk, what I want to do is that I want to write this Hamiltonian operator as expectation of, I mean, of certain terms that involve some randomness. Here and below, I mean, so my random variable is x. Okay, so I'm using this capital letter X to denote some randomness. It could come from many, many different regions, but you can, I mean, for now, it's not that important. You can just think about that. I mean, this is a definition so that at any time t, I can view my Hamiltonian operator as an expectation of something, okay, as average of some random variables. Okay. And now, I mean, so it's a time-dependent Schrödinger equation, right? And I think for the physicists and the chemists in the audience, it's kind of immediately clear what you need to do is just to, I mean, write down the propagator as a time-ordered exponential and expand it, okay? And this is, of course, the so-called Dyson series, and also for mathematicians, this is nothing but just Taylor expansion. Okay, and then this is the formula that you would get. I mean, so if you still feel a bit dizzy about these expectations, I mean, just think about this expectation as Hamiltonian, then this formula hopefully would look very familiar to you. Right? And for mathematicians, this is nothing but you just do a Duhamel principle and then substitute into the right-hand side the order, I mean, the equation that you have. Okay, so far so good, I guess. And now, I mean, the reason that we, I mean, kind of introduce these expectations is that now you see that immediately, I mean, because the right hand is a sum, right? And then I can, I mean, this is a high dimensional integral. If you think about, I mean, these, I mean, if you need this order to be very large, the M, okay, to kind of evaluate this, I mean, let's say that we are in the regime that cannot really connect the Hamiltonian, okay? And then, I mean, we can easily convert this to a Monte Carlo scheme, right, for time evolution. And so, I mean, so you just, what you need to do is that for each sample, what you need to sample from, I mean, so here I'm using this NP to denote the number of samples that we have. And for each sample, you need to sample the M, which is the order of the summation. And then for each time, I mean, then what you need to do is that for M, you need to sample all these times from T1 to Tm, okay? And for each of them, I mean, I denote this randomness by X, okay? So you sample some random realization of this A, so that average of them will give you Hamiltonian. And then if you do this many, many times, this would converge to, I mean, the Dyson series. Okay. And also, I mean, just to, I mean, kind of give a jargon so that I don't need to say this all the time, so that this is kind of be viewed as a Feynman approach, right? So essentially, you're doing a path integral, and then along the path integral, you're doing some random sampling. And you sample the path and then sum together them, where the NP is the number of. And it's clear that this is unbiased in the sense that if I take expectation, then I just get back the Dyson series. I mean, so as long as, of course, the samplings are independent. I mean, we're not trying to screw up the Monte Carlo estimate. Okay. But of course, as we know that, I mean, to understand a Monte Carlo sampler, I mean, the estimate, the thing that we should look at is the like the variance of the estimator, because by the central limit theorem, the thing would become essentially, the error will become essentially Gaussian with the variance given by the calculation. And I'm not going to bore you with the calculation, but you can try to estimate the variance, and this is what you get. Okay? And one thing now to point out is that, I mean, so you see that immediately that this variance would depends on this t and in an exponential way, right? So which may not be surprising that if you want to simulate this, want to calculate this dynamics for longer time, then the variance actually grows exponentially. Which means that if you want to maintain the same accuracy level, the NP, the number of samples that you need to take in this Monte Carlo sampling, also needs to grow exponentially. Okay, so that's essentially the very simple message that we get from here. And remember that we are thinking about the Hamiltonian evolution so that the solution is actually unitary. So the norm shouldn't change, but the variance grows exponentially so that we have to choose an exponential number of samples. Okay, and so it's very, I mean, I guess it's could be like too oversimplified, but to my understanding, this is the origin of the dynamical sign problem. Okay? Just because that if we think about the summation of these Feynman paths, the variance grows exponentially.
Yeah, Jianfeng, hi. Just one question. How pessimistic is this bound?
It's a very good question. I will come back to that. It's, I mean, it's very pessimistic, of course, because we, I mean, ignored all the cancellations. But in practice, if you really simulate this thing, then you observe that actually numerically the variance actually grows exponentially. I mean, it's maybe the rate is not as bad as this, but I mean the exponential growth is very hard to avoid. Okay, so now let me also, I mean, so now if we come back to this thing, right, and if we're not in this workshop, but in like a elementary course in numerical analysis, or I mean a ODE course, then of course this is not a thing that first comes to mind, right? So I mean to solve this equation, I mean what comes into my mind, I mean everyone's mind hopefully, is essentially, I mean why we just not solving this as ODE, right? Because this is ODE. So I mean we should, as I mean kind of taken in a first elementary course in ODE, the thing that we learn is that okay, maybe we should just discretize it using forward Euler scheme, as simple as it is, right? So that if we do that, I mean, this is the simple Euler discretization. And now remember that my Hamiltonian is come from an average of something, right? So, but I can just, I mean, instead of using Hamiltonian here, right, because I want to take this Monte Carlo samples, what I can do is that on top of this discrete scheme, I take a Monte Carlo average of this Hamiltonian. Okay, where I may use this NS as the sample that you take at each time step. And of course, this also gives us a scheme, right? This is a very natural thing. And I mean, if we do that, and now, I mean, if you simply calculate the expectation of this thing, you can see that obviously this algorithm is also unbiased, but it's unbiased in the sense that it's the expectation is equal to the discrete guy. Okay, so there was, of course, disposition error coming from the, the first step, but at least on the discrete level, this scheme is also unbiased. Okay. And now, because I mean the time step size, I mean we take is, let's say it's h. Okay, the total number of time is of course I mean the total time divided by the h. Okay, and the number of sample in this kind of Euler scheme or Euler approach is given by that. And I can do this as a Monte Carlo scheme, right? So it's just that I propagate the thing unitarily, and then each time step I do some sample of the Hamiltonian, and I take average. And I mean, similarly, we can try to analyze what's the error of this thing. And I mean, I'm not going to bore you with the calculation, but in the end of the day, I mean, the idea is, of course, very, very classical, right? As in numerical analysis, you try to estimate the one-step error and the one-step, the growth of the variance, and try to use 1-1. Okay? And then, I mean, I'm not going to bore you with calculation, but then you end up with this formula. Okay. And now let me put these two together, right? So one is a fancy approach from a physics point of view using the Feynman. Another is more like down-to-earth approach from a numerical analysis point of view using Euler. Okay, and now both of them are biased, And if you look at the variance, it looks that, I mean, both of them exponentially growing, right? But one thing I want to point out is that you see actually they are kind of different in a sense that this variance, so maybe let's go to the next slide. So this variance of the Feynman way of doing things, okay, so the exponential growth is kind of intrinsic, I mean, due to the sign problem. So it's actually not much related with what we do for this sampling, since even if the A does not really depend on any randomness, so it's just deterministic Hamiltonian term. And if you do it, I mean, of course, there was still a sampling because of the high dimensional time integral that we need to do. But if you do that, it's still there is this exponential growth. Okay? While I would argue that for the Euler Monte Carlo, this exponential growth is actually not intrinsic for the dynamical sign problem. I mean, it's kind of an error accumulation that we are kind of used to with the numerical analysis that applying the ground wire inequality, okay, for the forward Euler scheme. And in particular, that if you see that there was a variance here, so that if the thing is deterministic, then I would not have, such kind of, variance growth due to the accumulation. Okay, so it's actually specific to the integration scheme that we used here. It's an error amplification factor.
Can I ask a question here? In part, the accumulation is due to the fact that you're not using a symplectic scheme.
Yes. Yeah. I mean, you are going ahead of me. I mean, that's next slide. That's exactly the message. So, in a way, that the reason that I say that it's actually, it's not intrinsic to it as a dynamical sign problem. Approach for the Feynman approach is that it's actually associated with the scheme. So that, this estimate coming from this kind of single step propagation of error amplification, it's actually very particular to the Euler scheme that we choose. So in particular, for this simple problem, for the problem that I showed you on the first slide, if we choose something like a Horn method, which is symplectic, or any other symplectic method, then you can, do a more refined numerical error analysis and to show that actually there is no error amplification. Okay, so that, in the end of the day, you can control the error like this. So there was no exponential growing. Okay. So to some extent, the numerical sign problem, or dynamical sign problem that we're coming into here, is really caused by the problem that we're doing things like trying to sum over diagrams or trying to sum over the Feynman path. Okay, so this is sort of, the message. And now let me actually, coming back to a little bit to more physics. I'm not trying to advertise. We should use things using stochastic Horn, but let me try to give it a slightly different point of view of understanding this. So what's going on, or the trade-off between the so-called dynamical sign problem, which are coming from that you want to sum over these diagrams or the path integral, and the error amplification, if you think about, we just view this as numerical discretization. One can understand it more from a physical point of view through that actually, what we are so used to do in numerical analysis or the Euler scheme is, in this context, can be viewed as so-called partial resummation of the diagrams. Okay, so you may hear of these fancy words, in maybe tutorials or from physics more oriented lectures, but trying to say that you can understand these terms in a very simple context, even like ODE. Okay, so what it is, so let's consider about the second step in our Euler scheme, the evolution. And now, if you expand it, you realize that, this is our Dyson series as we expand, right? This is the expansion to the second order. And now you also kind of carry out the calculation in the Euler scheme to see what happens at the second time step. And you see that you get a very similar formula, except that if you're thinking about it in Dyson way, then all these things will be independently sampled. Okay. While, if you think about Euler, because since the encoded or resummed, in other words, in this U1 tilde, the numerical approximation, and then what it end up with is that you see this high order kind of approximation would actually reuse the randomness that is involved in the low order ones. And this, in fact, could help to cancel some of these kind of growth, the variance growing. Okay? Of course, for Euler, you still have this error amplification due to the Euler scheme, but if you use a symplectic scheme, then this actually completely cancels the exponential growth. Okay. So now this, so in a sense that, one of the if you understand this, then, for the rest of talk, you can essentially understand the message. is that in a certain sense, this partial resummation reduces the variance from the Monte Carlo sampling, okay? But as a price to pay, I mean, if you're not have a way to do a symplectic scheme or things like that, then it will actually, I mean, pays for the error accumulation for the numerical integration from the numerical propagation of the error. So this, I mean, in a very simple context, I mean, this is a trade-off. I mean, one can understand this trade-off between the so-called dynamical sign problem and, I mean, error amplification due to numerical schemes. All right, so now let's, I mean, talk to, I mean, come to the real thing, and then, I mean, and then I'll present these methods, and then maybe, then, I mean, there are some open questions that I think would be interesting to think about in this program. Okay, so now let's go to the real thing. Okay, so I'm thinking about dynamical problems for open quantum systems, and I mean, the usual model for open quantum system is that you have a system and you have a path, and there's some coupling between them. Okay, and written in the Hamiltonian, I mean, using tensor product, this is sort of a Hamiltonian given by the open quantum system. So this is the system part, this is the path part, and there was some coupling between the system and path. Okay, and I mean, if you want some concrete example in mind, you can think of the, for example, the celebrated spin boson model, where the system is just given by a two-level system. Okay, and then the path is a bunch of harmonic oscillators, and then they're coupled in a linear way. And of course, the challenge for open quantum system, which is also very similar to many of these embedding methods, the challenge is that just that we have too many degree of freedom of whole thing. I mean, in particular, the path has many degree of freedom, and we cannot afford that. And so the strategy, I mean, here is really to model reduction, so that we can hopefully restrict our computation just on the system part. I mean, that path part can be integrated out. Okay, and now I mean, there are many ways to do this, but I mean, the way that I'm thinking, I mean, is at least the framework. I mean, we are talking about diagrammatic method, and by diagrammatic method, I mean, the starting point is really time-dependent perturbation theory. Okay, and in this context, is actually I mean, easiest to present by starting with the von Neumann equation, which you have also seen in previous talks. So we're thinking about the von Neumann evolution of the density matrix, and we're thinking, I mean, that usually for the usual setup for time-dependent perturbation theory, I view this Hamiltonian as a reference Hamiltonian plus some perturbations, and we're interested in some time evolution of the observables, which is given by that. Okay, so it's just the trace of the observable with the time evolved density matrix. Okay, or written in this way. And now, if you start to do perturbation and to expand, and now, I mean, which is very similar to what we have done before, right? So because, I mean, the unitary evolution, now you can be represented by a Dyson series. Okay? So this is almost the same thing as before, except that, I mean, previously I dumped all the terms into W, but I mean, here, let's also keep the reference Hamiltonian part. Okay? So, I mean, this, if you still remember the first slide, I mean, this is really very similar to that expression. And then, I mean, what you can do is just plug in and then end up with this horrible formula, and which is very long. So that's why, I mean, the physicists invent these very nice notations to keep track of all these things. And in this case, for time-dependent problems, we get, I mean, these contours. I mean, this is a Kaddish contour. So what's happening, I mean, just to explain the graphical notation, what's happening is that from the time 0, okay, you propagate forward in time until time t. And then you propagate backward in time, because, I mean, remember that, I mean, we have such a thing, so that we need to propagate forward and propagate backward. Okay. And now the diagram here, I mean, the notation is just that for each of these dots, it means that I interact with W. Okay. I insert in W in each of these dots. And along these diagrams, that without, I mean, these lines means the unitary propagation using reference Hamiltonian. I hope the notation is clear. And I mean, so instead of writing down such a horrible formula, I mean, we can just represent it using diagram, okay, which is a really nice invention by Feynman and then by other physicists afterward. Okay, and now, I mean, we can just unify, I mean, this notation slightly. I mean, kind of make it slightly easier. I want to absorb this O into these unitary evolutions. And also, I mean, it's kind of hard to keep track of this time that going forward and backward. So let's just like rename the time so that it's instead of 0 to t back to 0, it's from 0 to 2t. Okay, and then you will get this. I mean, so this is just the renaming of what I I showed you before. Okay, and then I mean, we just introduced some fancy word. This is the so-called bare propagator, and the real thing that we want. I mean, so that in the end, the real thing that we want is the so-called propagator, right? And then this, with the interaction, and this is the propagate. This is the evolution without interaction for the reference Hamiltonian. Okay, and we, as I said, we unfold the characteristic contour so that it becomes a just a line from 0 to 2p. Okay, so now if we apply this, so is the formalism clear? I hope. So if we apply this, time-dependent perturbation theory to the open quantum system, what we do is that we treat the interaction as the perturbation. Okay, and I just apply the same thing, and now you can just write down the following the same thing, and then you follow. You kind of end up with these formulas, but they're not really nothing. You don't need to worry too much about these formulas, but the idea is really exactly the same. Okay, so that you just if there is no, it's kind of you're getting a perturbation theory, and then you have these propagators without interaction between the path and the system, and then you are applying perturbatively at these time points, you're applying the interactions. Okay, and so let me not bore you with these formulas, but I'm going to make a few assumptions to make our life slightly easier. Okay, so to reduce, because here, up to this point is still, a kind of, you still need to kind of evolve the coupled system, right? You're just kind of treating the interactions perturbatively, but these systems that you still need to evolve, and in particular, I still need to keep track of what's happening on the path. But then let's make a few, simplifying assumptions, which is quite common in the open quantum systems. So now let's kind of, make the assumption that our path, the initial state, actually commutes with the Hamiltonian of the path Hamiltonian, which means that if without interaction, the path state will never change. The path state was just stayed as what it is in the beginning. And also, we are making an assumption that the so-called Brick Theorem holds. So, for which, you can understand it as it's just that trying to simplify the terms that we will have here from these expansions, so that you need to keep track by applying this perturbation theory. If you do not making these simplified assumptions, you're going to keep track of this quantity, which is essentially the action of the path part of the interaction onto the path states after evolution. Okay, and this, in principle, this could depend on all these time interaction points from S1 to Sm. If you sum up to the mth order of the diagram, but then we want to just simplifying assumptions. We want to make our life easier. So, or you can think of that you're just making Gaussian assumptions, or it's equilibrium. So, but in the more general form, you can just think. Our assumption could be just that there is. It holds a kind of a Brick theorem for the evaluation of this path inference functional, in a sense that even though the path inference functional, kind of in principle, should depend on all the time points that you have in the diagram. But we assume Brick theorem in a sense that this can be decomposed into kind of products of 2-point correlations. Okay? I think, so these kind of language probably have been brought up already before in the tutorial, so that, but I will also, make it slightly easier using diagrams. Okay, so, so you do not need to know, how to reduce it. But after making these assumptions, you can actually evaluate that. So what you need to do, the assumption of the Brick theorem is essentially that for inference functions, I can evaluate them as a pair product. And then what I need to keep track of is then just how to pair them together, how to pair the time points together. And then, on the diagrammatic language, is that you just need to keep track of these arcs where the things are paired together. So that this means that the inference function, there was a product between the part given by S1 and S2, and then there was an inference, given by the current inference kernel given by S3 and S4. Okay, is that clear? All right. So now, in the end of the day, we're interested in the full propagator. Okay, because we are interested in, the evaluation of the evolution of the state and influenced by the path. And then we take the observable in the end. Okay, so this is kind of thing that we're interested. And now, we carry out, we denote this thing as the sort of full propagator. And this integrate out, you see that the full propagator integrates out the path degree of freedom. So in the end of the day, I mean, this you can think of this just as a propagation in the system. If you can keep track of the rho S, and if you know, I mean, what the G is, then you can evaluate the physical observables acting on the system. Okay. So in short, after all this machinery, what the language here is that, I mean, what you need to worry about is the propagator, okay, from time 0 to t. And let me also mention that, I mean, for mathematicians, this framework, I mean, of time-dependent perturbation theory and also these diagrammatic methods in time-dependent regime is much more friendly because you do not need to worry about convergence. As long as all these terms are bounded, I mean, for example, the inference function and so on, I mean, this is naturally absolute convergent, so that, I mean, you can change the order of these summations and so on, and without worrying about issues that you may face in the zero temperature case, which means that you need to propagate to infinity. Okay, and then a lot of things that will break down. Okay, so now, I mean, following very similar derivation as before, right? So that, I mean, so
Jianfeng, you hear me?
Yes.
Quick question. So where's W? So the W must appear somewhere.
The W is, I mean, so the full propagator, so that you need to evolve this using the actual Hamiltonian, right? So that, I mean, so this is actual Hamiltonian, which includes the W. This is just definition here. And then you need to, I mean, do the perturbations so that you can write the full propagator using the bare propagation, which is given by the U0 here.
And later, when you do this inchworm thing, some of this G's will be replaced by the renormalized G, which is still approximation.
This G is a bold line, if you like. So it is sum up together. So maybe I should come to this slide, then which become more clear. So diagrammatically, what's happening? So the thing that we want to get is the full propagator. And as I promised, that full propagator, once you have the full propagator, you can evaluate the physical observables. Okay. And now, I mean, the assumptions, of course, the full propagator is very hard to evaluate. So what we do is that we start to expand it using the perturbation theory. And in perturbation theory, I mean, I write down this formula. And what's happening here is that in the U part, you're only propagating using the bare propagator, which is the reference, and which actually decouples the system and the path. And the interaction or the inference of the path only comes in from the inference function. And in general, this inference function could be something that is very complicated, depends on all the time steps, points. And then under the Brick theorem or under the hypothesis of Brick theorem, and you can reduce it to these pair correlations. And so that, I mean, in the language of the diagrammatic sums, you can rewrite this as this following. Okay. So what is, I mean, this is the term that there was no interaction, okay? M is equal to 0, so that is just given by the bare propagator. And this is the first order perturbation in the perturbation theory, where, I mean, the where the path comes in, but only at 2 points, okay? And then this is second order, so you have these diagrams.
Yeah, this answers the question.
Yeah, and then I'm writing down, I mean, for if you want the Feynman rule here, so how to evaluate the right-hand side. So for each arc, there was a B, and then you product, and then for each line segment, there was a bare propagator. And then these black dots are the where W.
Okay, remind me the definition of B.
The B is coming from the inference function, so it captures the, so it's essentially, it's this, and then we assume that it can be written as a pair interactions. So in the case of, in the naive case of, for example, these bosonic, I mean, if your path is a bunch of harmonic oscillators, and then you can get explicit expressions for these. But I mean, only the structure is important here, so that, I mean, they are given by the pairwise products. So the particular formula of B, I mean, depends on the system. It could be Ohmian path, or it could be something else, but I mean, the structure is the same. Okay, so this is, I mean, so as I said before, I mean, everything here is rigorous, so that, I mean, you don't need to worry about convergence. I mean, so as long as everything is bounded, so that, I mean, you can this infinite series actually converge, and so it's essentially just a perturbation theory, but written in a diagrammatic language. Okay, so you can see that this is actually very similar in a way. I mean, even though that it may look kind of complicated from the first side, it's actually quite similar to what we have in the first place. I mean, so that it just, you're using the Dyson series expansion for a unitary evolution for a closed system. And then you start to pick the path, right? So in that context, you pick the S points that, in the interaction for the time. And in this context, it's slightly more complicated. So instead of, what you need to do is that you need to random pick an order, okay? And you need to pick these time points as before. But just the one more complication is that you also need to pick a diagram, okay? If you want to treat this like in the Monte Carlo fashion, in a random fashion. And this is essentially the so-called diagrammatic Monte Carlo method. Okay, so you expand this infinite series, which each term would involve a very high dimensional integral, okay? Because in principle, you need to integrate all the choice of this S for each order. And then you also need to sum this kind of, this different configuration of the diagram, which couple together, given like 2m 10 points, how would you pair them together and how to product? Okay. And everything can be treated Monte Carlo, and what you will get is very similar to what we showed in the toy example before, so that is kind of a diagrammatic Monte Carlo method. Okay. So now, if you really do this, and then you would, essentially face the problem that we had before, which is the so-called dynamical sign problem. And because so even though that here the analysis becomes slightly more complicated because it involves many terms, but you can do a similar calculation of the variance of this Monte Carlo scheme, and then you can, kind of convince yourself that the variance grows exponentially and very quickly. Okay, and so that. If you do the bare kind of Monte Carlo, just trying to sum together the right-hand side, treating this integral using the Monte Carlo way, quickly, you cannot afford the growth of the variance. And now the idea is actually, trying to, the main idea behind the algorithm that was proposed, by Andy Millis and David Reichman and his collaborators, Emmanuel Gao. So, and in fact, like 10 years ago, the idea is essentially trying to reduce the variance, okay? And now, of course, they are presenting this in a kind of a physical language. So in the sense of trying to do the resummation of diagrams, and or in the word of this Luttinger Ward kind of thing is trying to use the both diagrams on the right-hand side to kind of do resummation and to, to reduce the variance, okay? And now what I want to kind of present, or what our understanding of the algorithm is that, in a certain sense, you can understand this as also very similar to the Euler scheme that I talked to before. It's, in a certain sense, this resummation is trying to view the problem, or this Feynman kind of diagrammatic expansion problem, as an ODE, and trying to just use a numerical ODE solver for these kind of things. But of course, the story becomes much more complicated in the open quantum system. Okay, and in particular, it's unclear, which is the kind of a very big challenge for us, and we still do not have a clue, is how to apply the symplectic scheme. Okay, which I hope there are people in the audience who would have better ideas. Okay, so let me proceed, and let me actually skip this and just mention that it's actually very similar to the so-called bold-line diagrammatic Monte Carlo methods, even for ground state. Okay, and now the idea of the inchworm, okay, which I kind of summarize in this theorem in the diagrammatic representation, which, by the way, we can prove all these things rigorously, but I'm not going to work too much about proof, but I'm trying to show you the idea, is that, so you can, the right-hand side, instead of expanding, just using the bad propagators and with these path inference functions, okay, you can actually reuse, or you can expand the series in using the bold-line diagrams. Okay, and this is in a way that, the inchworm resummation comes in, and the idea realized by these physicists. And so where you, on the right-hand side, you see that difference is that you're using these bold-line diagrams, okay? But then there is a restriction that you need to, because you're doing resummation, so that you are restricting the kind of diagrams that you are sum over. So there are things that are not proper, okay? So let me actually explain what that means. So the proper diagrams, okay? So the inchworm expansion, or this diagrammatic expansion by reusing the bold line, is I mean, by the way, for the mathematician in the audience, I mean, don't worry, I'll come back to a more friendly interpretation of what's going on, okay? Is that, I mean, if you realize these diagrams, and there are a few things that is not inchworm proper, in a sense that if you kind of just, I mean, so you start with this kind of thin line diagram, and you're replacing these thin lines with bold lines, okay? And up to certain points, okay? So this is from the point that, let's say we have already finished the computation and we obtained the bold line diagrams, okay? And now you start to kind of link together, I mean, by this, the inference function from the path, okay? And now naively, I mean, you just do all these diagrams. But then if you realize that because in principle, the bold line has already taken into consideration of all the inference from the path. So that this would incur some double counting. Because I mean, this seems think that, okay, so I'm still thinking about inference between of the path from S1 and S2, but this should be already taken into account because I'm already using the bold line. So that this thing diagram should not appear, but it should be already included here. And similarly, if you have some kind of dangling diagram like that, it should be also included. But this one is different because here you're still using the propagator. I mean, this thing, I mean, the information we are not already calculated. And so that this thing should be included, okay? And similarly, I mean, here, so that you see that this one, because it's kind of a isolated diagram, that isolated pair that is kind of in between these bold lines, so that this should be already also kind of captured by this bold line propagator, by the exact propagator. Okay, so this should be also included. So that, I mean, the only proper diagram that, I mean, for this resummation is only these diagrams that with interaction, either from the sites from here, or that, I mean, you have these links that integrated with that so that this thing is not isolated. So you cannot replace this by a bold line because, I mean, there is another point in between which links to the part that is not yet propagated to. Okay, and also this kind of thing is so. Okay, so I mean, in this language, this becomes kind of, I mean, at least for mathematicians, it becomes complicated. But if you think about the analogy with Euler scheme, what this says is just that, I mean, for the Euler propagation, if you are not at the time step n, you should just directly use the result at time step n-1. And you should not think about all these propagations that beforehand. Okay, and in particular, if you think about, I mean, the in a more mathematically way, I mean, actually, this is a theorem that kind of rewrite it in a mathematical sense. I mean, let's actually skip these things. And now, I mean, using mathematical terminologies, but now from a more ODE point of view, one can think of that actually what the inchworm is doing is essentially viewing this original equation of the diagrammatic equation as the integral differential equation. Okay, so this is the integral differential interpretation or reformulation of the inchworm method that was proposed by us. And the idea is just that. So, I mean, compare with the bare propagation that we have before, or I mean, if you don't have this interaction with the bus, if you just have a system, okay, so remember that we have before that, I mean, so if you think about the actual evolution equation for the quantum system, I don't know what's happening with my pad, sorry. So if you have, there was no interaction with the bath, you will just have a very similar evolution equation as we had before, which is kind of ODE. But now, because of the bath inference, you need to introduce all these kind of integral terms that is history dependent, which captures these diagrams that in inchworm proper diagrams that interacting with the previous history. Okay, so there's these kind of integral terms that incorporating these inchworm proper diagrams that kind of interacting, I mean, capturing the influence of the path. Okay, and now this ODE representation, I mean, so it's kind of the detail is complicated, and I don't think I want to go into the details here. But one of the advantage of this ODE interpretation is that it gives a natural way to compare or to think about, I mean, these variance reduction or the variance calculations. Because now, I mean, first of all, it suggests a very natural numerical scheme. Because, I mean, so this is an integral differential equation, right? So we can just integrate this, I mean, discretize this using an ODE, numerical ODE scheme, and then do sampling of this term using Monte Carlo. So which is kind of similar to the Euler Monte Carlo scheme that we talked about before. And it turns out that this is essentially the inchworm numerical method for the inchworm. Okay, I mean, which is correspondent. So that this is a numerical scheme. So what we do is just that we want to solve this. And now you see that this time, which is the time that in the inchworm diagram, I mean, for people who are familiar with this diagrammatic language, this is time that you starting the bold line propagation and up to this time. Okay. And in this inchworm algorithm, or from a numerical analysis point of view, what it's doing is just that for this term, or for this time that you are using the history, you're treating that in a numerical ODE way. So for example, this is not the only choice. One thing we can do is using a Hoyle method because it's symplectic, at least for this term, which is nice. Okay. And then for the other term, it involves these high dimensional integrals because it involves these diagrams, for example, linking the past history, by the path inference. And these are high dimensional integrals, and also it involves these diagram summations. And what you can do is just that you sample these things using a Monte Carlo scheme. Okay. And now because of this resummation, you are kind of encoding a lot of these diagrams into these Boolean diagrams. So even though that this also looks like an infinite series expansion, but in practice, what one can find is that the order that one needed is much smaller compared with the bare sum of the diagram, okay, of all these diagrams. So even though that the number of diagrams here also grows, first of all, the inchworm, as we mentioned before, that the inchworm diagram reduces the number of diagrams one needs to consider because not all of them are proper. But if you count the scaling, actually the scaling does not really change much. And if the M grows fast, scaling of the inchworm diagram is also a double factorial M. But the hope is that, so because of this resummation, so that we don't need to sum over to very high order. And also the hope is that because of this resummation, there will be already some cancellation that comes in, which reduces dynamical sign problem. Okay. And the thing that we can capture is the error estimate of the propagation of the variance is captured in the following theorem that one can prove. So that you still see a growth of the by the way, I should mention that even so because of this open quantum system, if you actually do not have if you do not reduce the variance, the growth is actually even more terrible than exponential growth. It's actually double factorial. And so now what one can prove, at least for this numerical scheme and using what we currently have, is that if you truncate the inchworm diagram or this integral differential equation up to the order M, then the error growth you can control, using, by the right-hand side is this. So the variance still dominates the error, and you still see some exponential, super exponential growth. Okay, and but the hope is that for small m, at least, this growth is more milder than the original diagrammatic expansion. Okay, so there is still a trade-off between the error amplification and the resummation here. So the resummation reduces the order here. Okay, so that the growth, the amplification, the dynamical sign problem is tamed a little bit, but still it introduces, the error amplification from a numerical scheme. Okay, because you can think of easily as because you're reusing these partial summation that you have from the bold line, so that these errors that are from the previous thing will accumulate. Okay, and now this naturally, okay, maybe let me show you some numerical examples. So that this actually, if you truncate to the first order, it's exponential. If you truncate to the third order, it's actually square. And you can see numerically, it's actually very, we are numeric. I think before maybe Eric was asking that whether these estimates are so pessimistic, but actually numerically what we observe is that at least for inchworm, these numerical estimate of variance is, fits very well with what you observe numerically. Okay, at least for a spin boson system with ohmic electrical density. So it naturally leads to the question that whether, one can do something better. Okay, so, maybe it's kind of sounds pessimistic because, it's like even worse than exponential. But let me, argue also that, so that this worse than exponential thing is, is not an artifact of our estimate. It's because these nonlinear interactions of these integral differential equations. Because if you only have a differential part, this thing is linear. But because of the introduction, these diagrams and then the nonlinearity comes in from these diagrams using these bold line things, that actually these, the error amplification, coming from these nonlinear terms also, so that it will actually make the error amplification worse. Okay, even though that we can still control them and it fits numerically well, but it does seem that it's actually worse than exponential. Okay, so I think my time is kind of up, so let me actually skip these numerical examples. But one thing that I really hope that is possible to be resolved, or possible to make some progress, is that so I think our estimate is kind of sharp for the error amplification. At least for numerical scheme that we have. So remember that for the ODE part, we're using the Hoy method, which is symplectic. And then for the diagram, you don't have much choice, so that has to do some Monte Carlo. So there are some ways to do the Monte Carlo more efficiently by some reduce the cost of the number of diagrams that you need to do, for example, using inclusion-exclusion principle, and also using some fast kind of calculations that we are working on. We have some more recent papers on that. But the scaling cannot really be improved in a way that it does involve summation of a lot of diagrams. And so in particular, that this growth that we can obtain by this numerical scheme is is t to the m. So it's kind of related with the truncation order. And so in particular, that if you need to use a very large m truncation order, this kind of error amplification is really quite unfavorable. Okay? And in particular, if you do not truncate, it will become double exponential. Okay, and so this actually becomes much worse. So there is a trade-off between error amplification and dynamical sign problem, so that if you do the inchworm but keep very large order, asymptotically, actually error amplification will kill the even overwhelm the dynamical sign problem. Okay? So this naturally leads to a question that is it possible to design a better numerical integration scheme? Okay, because as we can see in the first, for example, the error amplification there, if we use a naive Euler scheme, it's actually terrible. But it's very simple to, to kind of change the numerical scheme by using a, Hoy method symplectic algorithm, and one can actually prove that there is no error amplification, which is also kind of expected. The structure here is, of course, kind of more delicate, because it not only involves the first part, which is the interaction, without, so the first part here, which is the integration or the evolution without interaction with the path, okay? But then there was this horrible nonlinear mass that, coming from the diagrammatic summation that comes in the right-hand side, okay? So, this is kind of a question that we still do not know how to deal with, even though we are kind of thinking in the general context of open quantum system, how to design numerical schemes to explore the nature or the structure of these open quantum systems. In particular, as we know that, because if we view this as open quantum system, if you think of this as a quantum channel, the quantum channel should be CPTP. It should be completely positive and trace preserving. And so there should be some kind of damping. So there should be some structural information there that hopefully one can use to design a better numerical scheme and to suppress the error from the error amplification. But unfortunately, so far we still didn't find a way to do that, even though that the inchworm is, I think, is a very good framework to start thinking about that, at least on the differential equation level. It's actually equivalent with the original propagation, and it has fewer terms, to sum over. So in principle, one can think of this as a good kind of starting point as what we do in the numerical ODE, starting from the Euler scheme. But then what would be a good numerical scheme to integrate that, and also what would be a good framework to do numerical analysis? I think this, it's kind of a very exciting questions, and I hope there will be some ideas maybe from the program participants. Okay, and with that, let me conclude here. I think my time is up. And if you want to read more, this is a very, I think, high-level presentation. But if you want to read more details, it's all included in these references. And the first one introduces this, at least the mathematical way of thinking about these diagrammatic algorithms and the inchworm Monte Carlo algorithms in the integral differential equation formalism. And then this one, we trying to do the error analysis of trying to analyze these, distinguish the sign problems and also the error amplification from the numerical scheme. And then these two are more algorithmic, like how to accelerate these computations by using some computational tricks. Okay, thanks a lot.
Thank you very much.